You walk into your local coffee shop, flip open your laptop, and before you even take a sip of your latte, you're online. We've come to expect this connection as a baseline standard for daily life, a process that feels instantaneous and nearly invisible. But beneath that user experience is a rigid, highly orchestrated set of rules. Network borders are incredibly strict. You can't just show up and expect other devices to communicate with you. To cross that border, your device needs a specific set of credentials. First, an IP address. This is the identifier for your exact device, acting like a house number on a street. Second, you need a subnet mask. This identifies the local neighborhood boundary, telling your computer which devices are on your local street and which are out on the broader internet. If the data needs to leave that local street, it heads to the third credential, the default gateway. It's the specific router your device must talk to if it wants to venture out onto the global internet. Without these three mathematical coordinates, a device is functionally invisible, completely isolated from the rest of the world. Historically, acquiring these credentials required static addressing. This is the manual baseline where a human administrator is responsible for assigning each identity. This interface shows the level of detail required. To get a device online, an IT worker has to manually select "Use the following IP address" and type out the IP address, subnet mask, and default gateway number by number. Static assignment is still necessary for infrastructure that needs to be found in the exact same location every time, like office printers or file servers. If those addresses changed randomly, clients would lose access. But human input is fragile. It's incredibly easy to mistype a single digit, entering a 33 instead of a 32. Because computers only perform basic error checks, they accept the mistake immediately. If another machine on that floor already owns the 33 address, you've created an IP conflict. Two devices are now asserting the same identity, causing data packets to drop and the network to functionally grind to a halt. Relying on manual spreadsheets to manage thousands of phones, laptops, and tablets is physically impossible. The scale of modern connectivity requires a move away from human entry. The shift starts when the user selects "Obtain an IP address automatically." Notice how the numerical entry boxes immediately gray out. The device is now locked, preventing any manual typos from entering the system. Responsibility for those coordinates passes to the Dynamic Host Configuration Protocol, or DHCP. It acts as an automated landlord, taking over the task of assigning and managing IP configurations. This protocol scales across our entire infrastructure. ISPs use high-capacity DHCP servers to manage IP addresses for neighborhoods, but the exact same protocol runs on small wireless routers in residential living rooms. The hardware is smaller, but the logic remains identical. Regardless of the network size, every DHCP server executes the same formalized negotiation before a device is allowed to communicate. Let's slow down the fraction of a second between tapping a Wi-Fi network and successfully connecting. This is the DORA process, a four-step sequence that happens in the blink of an eye. Step 1 is Discover. Your device broadcasts a distress flare to every device in range, asking for a DHCP server. Step 2 is the Offer. A server hears it, checks available addresses, and replies with a proposal. "I can lease you this IP configuration." Step 3 is the Request. Your device formally accepts the offered address. This is vital because multiple servers might offer different addresses at once. By requesting one, the client tells the backup servers to return their offered addresses to their pools. Finally, Step 4 is Acknowledgement. The server finalizes the deal in its database and sends a message confirming the IP is yours, along with your subnet mask and gateway. This choreographed loop happens so fast it feels instantaneous, but it mathematically guarantees that every device has a unique identity without human intervention. There is one specific condition to this automation. You don't own that IP address. It is strictly leased to your device for a limited window of time. This chart highlights the problem. The standard IPv4 system only has about 4.3 billion unique addresses globally. Meanwhile, there are tens of billions of connected devices in the world. If public Wi-Fi networks issued permanent addresses to every smartphone that walked past, they would run out of digital real estate in a matter of days, locking out any new users. The solution is the DHCP recycling pool. When your device disconnects or you leave the building, the IP address is revoked and returned to the pool, ready for the very next person who walks through the door. This cycle of temporary leasing and recycling is what allows networks to handle massive volumes of visitors without ever running out of addresses. It is the foundational mechanism of modern digital mobility. But consider the timing. If network access relies on these expiring timers, what happens if you're streaming a movie and your 24-hour lease hits zero right in the middle of a scene? The video doesn't stop. Somewhere in the background, your device and the server keep the connection alive, renewing the paperwork while the guest is still in the room. Right now, your living room is a chaotic data environment. A smart TV streams 4K video, a phone pulls down app updates, a laptop syncs files, and a thermostat pings a server. Dozens of devices are generating thousands of independent packets every single second. But to the outside global internet, none of these individual devices actually exist. They are all sharing one single public identity. The entire architecture of the modern web relies on this brilliantly orchestrated illusion. To prevent that collapse, there is a rigid, highly regulated checkpoint operating right inside your house, the standard edge router. To understand how your local devices actually reach the outside world, we are going to mechanically trace a single packet's journey to deconstruct how routing boundaries and multiplexing processes truly function. Without this highly regulated bottleneck, the transition from a localized broadcast domain to the sprawling infrastructure of the internet backbone would fail entirely. The foundational rule of networking is strict. A device cannot natively route traffic outside of its own subnet. If a destination IP is foreign, the device is locked in. Before a single packet ever leaves the network interface card, the host operating system has to make a definitive routing decision to determine if the target is local or distant. It uses the subnet mask, converting the destination IP and its own mask into binary sequences. It then executes a bitwise ANDing operation, a side-by-side comparison of the network bits. If they don't match, the system knows the destination is foreign and halts local searches. Instead of dropping the packet, the system wraps it in a layer 2 frame, physically addressed to the MAC address of the default gateway, the router. This means that if a host doesn't know the exact local IP address of that router, the strict mathematical isolation of the subnet renders the device completely deaf and mute to the outside world. But when a new device first joins a network, it faces a paradox. It needs the default gateway's IP to communicate, but on boot up, it lacks an IP address itself to even ask for it. Lacking a network identity, the device bypasses the IP protocol. It uses its hardware MAC address to scream a physical broadcast across the local switch. This negotiation sequence is known as the DORA process: discover, offer, request, and acknowledge. The router, acting as the DHCP server, receives the broadcast and offers a payload back to the client. As shown here, it provisions the IPv4 address and subnet mask. Crucially, it maps its internal IP, 192.168.1.1, as the default gateway, declaring itself the subnet's exit node. The host now possesses a fully mapped local identity. However, this specific class of private IP address is entirely non-routable on the public internet. The 192.168 addresses dispensed by the router fall under a mathematical designation known as RFC 1918 private address space. Internet backbone routers are explicitly programmed to instantly drop any packet bearing an RFC 1918 address. They are mathematically forbidden from traveling the global web. To bypass this, the router operates as a split-brain system. On the internal, right side, it dictates architecture and hands out private addresses. Facing the outside ISP, it flips roles, acting as a DHCP client to receive a single, universally routable public IP address. The router now holds two distinct identities. But simply connecting these two domains physically is not enough. If the router passed a private packet directly out of its WAN interface, the internet would instantly destroy it. Let's isolate a single outbound HTTP request, leaving a local laptop, heading for a public web server. If the router simply stripped the private IP and swapped in its public IP, the system would crash the moment a second device went online. When the web server replied, the router would have no idea which internal device actually asked for the data. To prevent chaos, the gateway uses port address translation. The router strips the private source IP, replacing it with its public WAN IP. It generates an ephemeral port number, combining them into a claim ticket that is permanently recorded in a stateful translation ledger. Finally, the hardware recalculates the IP checksums to ensure the packet is mathematically valid and blasts the forged frame out to the ISP. The router has successfully stolen the packet. It has completely obscured the internal network layout and presented the request to the world as if it generated the data itself. When the response returns from the global web server, it strikes the router's WAN interface, addressed solely to that single public IP and the ephemeral port. The router instantly consults its memory, checking the inbound port against the stateful ledger. Finding an exact match, it reverses the process. It strips the public headers and rewrites the destination back to the laptop's private IP and internal port. It recalculates the checksums one last time and forwards the payload across the local switch directly to the specific hardware that requested it. The computational speed is staggering. The hardware dynamically opens and closes port mappings, performing ledger lookups and header rewrites thousands of times per second. This dynamic, high-speed resource allocation is what seamlessly multiplexes an entire household of hardware behind one identical public identity. Because NAT naturally drops unsolicited inbound traffic, it is widely misunderstood as a purpose-built security firewall. But NAT is not performing deep packet inspection. It simply drops inbound data because it lacks a matching translation map in its ledger, not because it is actively neutralizing a threat. The true origin of this system is architectural exhaustion. The original 32-bit IPv4 architecture mathematically capped the internet at roughly 4.3 billion public IPs. We ran out of those addresses years ago. Port address translation is essentially a structural hack, designed to keep an obsolete, exhausted protocol functioning in a world with billions of devices. The permanent solution is the 128-bit architecture of IPv6. It provides a pool of addresses so massive that every single phone, television, and sensor on Earth can be assigned its own unique, globally routable IP. When IPv6 finally eliminates the need for address translation, the long-standing illusion of the private local network will vanish. Every device will stand exposed to the global web, forcing a massive re-engineering of how we secure the edge. You open your laptop, click a browser icon, and a video call appears. The user experience is perfectly calm, but underneath that glass screen, your hardware is being bombarded by millions of electrical pulses every single second. Your computer is simultaneously pulling down high-definition video frames, pushing an outgoing audio stream, checking a background email server, and downloading a software update. All of this data arrives as a massive, high-speed scramble of physical signals, yet none of it collides. Your emails do not end up inside your video call. A single IP address cannot maintain this level of organization on its own. The hardware relies on a highly specific, multi-layered targeting architecture. To see exactly how your device sorts this digital chaos, we have to track the mechanical sequence of a single data transmission. We have to follow the encapsulation process from the physical layer, through the logical layer, and finally up to the transport layer. Every device connected to an Ethernet network operates with a dual identity. First, it has a logical IP address, which handles end-to-end delivery, like a zip code guiding a letter to a specific city. Second, it has a physical MAC address, permanently burned into the network interface card, which handles node-to-node delivery on the exact same local network. The simplest way to see these identities interact is to look at two computers communicating on the exact same local area network. This table breaks down the specific addressing required for a local jump. Notice that the packet contains both the logical destination IP address of PC2 and the physical destination MAC address of PC2. Before PC1 can push this data out onto the cable, it encapsulates the Layer 3 IP packet completely inside a Layer 2 Ethernet frame. That outer frame is addressed explicitly to PC2's unique MAC address, shown here as 555555. Because the destination IP address is local, the physical MAC address is the only piece of information required to complete the final, direct handoff from one network interface card to the other. But an immediate problem arises if a device only knows half the equation. Most network applications operate using the logical IP address. In this diagram, host H1 knows the exact IPv4 address it wants to reach, 192.168.1.7, but it has no idea which specific device on the network actually owns that IP. Without the destination MAC address, the hardware cannot build the Ethernet frame. The network resolves this missing variable using the Address Resolution Protocol, or ARP. Step 1. The sending host generates a broadcast frame containing the target IP address and sends it to a generalized MAC address composed entirely of Fs. This all-ones format acts as a local loudspeaker. In step 2, the central switch receives that broadcast and forwards it to every single connected machine. Each device checks the requested IP against its own. Only host H3 has the matching IP, so it replies directly to the sender, providing its unique MAC address. For step 3, the sending machine takes that newly discovered MAC address and stores it alongside the IP in a local cache, known as the ARP table. Caching this relationship allows the sender to immediately build the physical Ethernet frame for future transmissions. It eliminates the need for constant, noisy broadcast queries and keeps network traffic highly efficient. That ARP broadcast process works perfectly for small offices, but it has a hard scalability limit. If a network expands to include hundreds of machines, relying entirely on Layer 2 broadcasts will eventually overwhelm the switches with constant query traffic. To prevent this congestion, administrators introduce routers. A router refuses to forward local broadcast frames. By placing a router at the center of the network, we establish strict boundaries, dividing one massive, noisy system into isolated, manageable broadcast domains. This alters the delivery mechanics when a target IP address sits completely outside the local domain. If PC1 wants to reach a remote server, it addresses the outer Layer 2 frame to its local default gateway, the router. In this table, you can see the destination IP belongs to the remote network, but the destination MAC address of BBBB belongs directly to router R1. When router R1 receives the frame, it strips away that old MAC header entirely. It reads the inner IP address to determine the most efficient path, and then encapsulates that IP packet inside a brand new data link frame addressed to the next router in the chain. This cycle repeats at every single intersection until the packet reaches the final local network. There, the last router encapsulates the packet one final time, applying the actual physical MAC address of the destination computer. This establishes the core rule of routing. The logical IP address dictates the final destination and remains static. The physical MAC address dictates only the current physical link, and it is actively rewritten at every single hop. The moment the packet reaches its final destination IP, the routing process ends and the transport layer takes control of the payload. The transport layer relies on two primary delivery protocols. The first is Transmission Control Protocol, or TCP. TCP breaks the data into individual segments, assigns a numbered sequence to each one, and demands a return acknowledgement for every single delivery. If a segment goes missing, TCP halts the process and resends it. The alternative is User Datagram Protocol, or UDP. UDP prioritizes raw speed over perfect reliability. It operates on a best effort architecture that completely ignores return acknowledgements, continuously throwing the data at the destination as fast as possible. The application dictates which protocol is required. If you are downloading a software update, a single missing byte will corrupt the executable file, making the rigid tracking of TCP mandatory. But if you are on a live voice-over IP call, dropping a tiny fraction of audio is vastly preferable to the compounding lag that would occur if TCP constantly paused to fetch missing data. Whether the data arrives via TCP or UDP, the computer faces one final sorting problem. It has thousands of incoming segments and needs to route them to the correct local application. It has to distinguish a web page refresh from a background email synchronization. To solve this, network architectures rely on standard numerical doors called well-known ports. When your browser requests a standard web page, it targets port 80. When your machine requests a file transfer via FTP, it targets port 21. These numbers explicitly identify the server service being requested. At the exact same time, the client machine dynamically generates its own temporary private port number, something like 1099. It attaches this private port to the outgoing request to serve as a precise return address. Combining the source IP and the dynamic private port with the destination IP and the well-known port creates what engineers call a socket pair. By assigning a unique socket pair to every single request, a single IP address can track and manage dozens of simultaneous application connections without a single packet colliding. IP professionals track connections using the command line utility netstat. Executing netstat with the NATP flag displays active socket pairs in real time. In this terminal output, the IP address and port syntax populate the local and foreign address columns, clearly separated by a colon. When a row displays an established state, it proves that a connection has been verified and data is actively flowing back and forth across that specific socket pair at this exact moment. Security professionals audit this specific output because it reveals the exact state of the network. An unexpected, established connection on a private port points directly to an unauthorized application communicating with a foreign IP address. Every single seamless interaction you have online relies on this complex sequence of IP, MAC, and port tracking. Right now, this flawless multiplexing on IPv4 networks requires the heavy, noisy ARP broadcasts examined earlier. However, the imminent adoption of IPv6 and its neighbor discovery protocol will soon replace those broadcasts entirely, establishing a more efficient mechanical standard for the future of network targeting. You click a button in New York, and a 4K video stored in Tokyo begins playing on your screen a fraction of a second later. This feeling of instantaneous delivery is made possible by a massive, deeply orchestrated mechanical infrastructure. Without it, the staggering volume of global data would collapse into immediate gridlock. To understand the engineering involved, imagine a small, isolated village. If you want to visit the local tavern, you look around, spot its distinct red door, and walk right up to it. This is a local area network, or LAN. It operates at layer 2, where devices communicate directly using their physical, hardwired identity, the MAC address. This local connection is fast, specifically because the village has no internal borders or checkpoints. When everyone is in the same room, data doesn't need a passport or a complex routing decision to find its destination. This high-speed, closed-room performance is exactly what defines our baseline expectation for how every single digital interaction should feel, which raises an obvious architectural question. If direct local connections are the fastest way to move data, why don't we just build the entire internet as one massive local network? A single global room would theoretically lower hardware costs, remove administrative borders, and allow every device on Earth to talk to every other device directly. But the fatal flaw in that design lies in the specific mechanism local computers use to find each other, the Address Resolution Protocol, or ARP. When a laptop needs to send a file to a printer in the same room, it doesn't know the printer's location. It has to scream a broadcast message to every single device plugged into the local switch, shouting, "Who has this specific IP address? Reveal your physical MAC address." Every machine in the room hears the shout, and only the target answers. While this screaming protocol works in a small office, attempting to scale it to billions of devices triggers a catastrophic failure. Imagine a stadium of people standing and screaming names to speak. The result is a paralyzing wall of noise. This is a broadcast storm. Millions of devices screaming for addresses instantly choke the infrastructure. In this giant room, there is also no way to manage quality of service. Without internal boundaries, a massive file download can easily drown out a priority video call, leading to constant stutters. Security also vanishes. In a single flat network, every device is exposed to every other device. If one machine is compromised, the attacker has a clear line of sight to every other machine in the organization. A single global network would result in a system paralyzed by its own scale, leaving every connected device vulnerable and gridlocked. To solve this, engineers divide the room by building hard physical walls. This diagram shows Router 1 acting as a central boundary segmenting independent networks. It acts as a strict border patrol, physically blocking local broadcast streams from crossing into neighboring networks. For a device to send data outside its local village, it must use a designated exit door called the default gateway. As seen here, every host on the local network points to this specific router interface to reach the remote world. When the data reaches this border, the router performs de-encapsulation. It takes the local envelope built by your laptop, rips it open, and reads the permanent global IP address inside. The router then consults its routing table, a constantly updated map of the internet, to determine the best global path to the destination network. If the destination network isn't in that table, the router follows a ruthless incinerator rule. It destroys the data immediately to prevent unknown traffic from looping endlessly across the globe and suffocating the system. The global highway remains functional because routers enforce these strict boundaries, partitioning local chaos and purging lost data before it can trigger a systemic collapse. From a global perspective, your data is involved in a high-stakes relay race. To reach its destination, a single packet must navigate across dozens of these segmented remote networks. At every single stop, a router must tear off the old envelope, check its routing tables, and build a brand new local package for the next leg of the journey. This mandatory border control introduces a physical time delay at every hop. Network engineers call this latency. Every piece of data we send is subject to this highly regulated architecture, moving through a series of friction-heavy checkpoints to ensure it doesn't destabilize the whole. A functional global network relies on this calculated trade-off. We accept a microscopic time delay at every toll booth to prevent the system from collapsing under its own weight.
Right now, your device is processing a massive, chaotic influx of data. You might have an active file transfer, a background DNS query, and multiple streaming browser tabs open all at the exact same time. The network relies on Layer 3 IP addressing to navigate the internet and deliver these packets to your specific machine. But the IP address stops at the front door. It lacks any mechanism to determine which specific application requested which piece of data. If your operating system lacked a rigorous internal sorting mechanism, an incoming chunk of a binary file download could route directly into an active web browser session, instantly corrupting the interface. The transport layer solves this exact problem. Sitting directly above the IP layer, it provides the critical endpoint multiplexing necessary to keep concurrent applications isolated. To map how a machine survives this continuous data bombardment without corruption, we have to look at the exact mechanics of transport protocols, the categorization of ports, and the mathematical formation of socket pairs. Before incoming data can be sorted into distinct application buckets, the system must establish the baseline delivery mechanics using either TCP or UDP. TCP, or Transmission Control Protocol, is the high-integrity transport option, engineered for processes where data loss is unacceptable. To transport a massive file, TCP breaks the data down into smaller, manageable segments. It then assigns a strict mathematical sequence number to every single piece. TCP also demands a receipt. If the sender does not receive an acknowledgement within a specific time window, it consults its ledger and resends only the specifically identified missing segment. This protocol guarantees structural integrity for things like FTP downloads and secure web traffic. But that constant two-way verification introduces high computational latency and network overhead. UDP, the User Datagram Protocol, is the exact architectural opposite. It is a stateless, best-effort delivery system designed entirely for speed. UDP drops packets at the destination IP with zero sequence tracking, no ledger systems, and absolutely no acknowledgement requirements. If a packet drops during a live voice call, the protocol simply keeps moving forward. Network architecture forces a strict choice. Engineers must select either the guaranteed structural integrity of TCP or the raw, unverified speed of UDP, based solely on an application's tolerance for data loss. Once a segment arrives via either TCP or UDP, the operating system requires a numerical identifier to route it to the exact software process waiting for it. This specific numerical identifier is called a port number. It is embedded directly within the header of every single incoming and outgoing network segment. This diagram shows the structural relationship between application protocols and numeric ports. HTTP points to port 80, SMTP to 25, and DNS to 53. These assignments act as funnels, dropping application traffic into the correct TCP or UDP transport mechanisms. Without global, rigorous standardization of these numerical assignments, a web server would have no way to distinguish a browser request from an incoming email, causing cross-network communication to instantly fail. To maintain this structure, the Internet Corporation for Assigned Names and Numbers, or IANA,
categorizes the entire spectrum of available ports, ranging from 1 to 65,535. The first tier contains well-known ports, spanning from 1 to 2023. These serve as permanent, universally recognized destination doors for core internet services, like standard HTTP and SMTP. The second tier covers registered ports, from 1024 to 49,151. Organizations utilize this block to lock in explicit routing for proprietary applications. The final tier contains private ports, spanning from 49,152 to 65,535. A client operating system dynamically generates these on the fly to act as temporary return addresses. Combining rigid, well-known destination ports on the server side with dynamic, disposable private source ports on the client side provides the exact mathematical framework required for concurrent communication. We can now link these two routing mechanisms. Layer 3 IP addresses navigate the external network to find the correct hardware, while Layer 4 port numbers navigate the internal operating system to find the correct software. String of a Layer 3 IP address and a Layer 4 port number is defined as a socket. A single socket is useless for two-way communication. The network requires a socket pair, a complete mapping that combines the sender's full socket with the receiver's full socket. This architecture diagram maps a client PC at 192.168.1.5 executing simultaneous web and FTP requests to a remote server at 192.168.1.7. Look at the bottom web connection path. The client dynamically generates private source port 1099, targeting the server's well-known HTTP port 80, logging the outgoing socket pair. Simultaneously, on the upper FTP connection path, the client generates source port 1305, targeting the server's FTP port 21, establishing a completely unique socket pair. When the server processes these requests, it reads the dynamically generated source ports 1099 and 1305 and uses them as precise segregated return addresses for the returning web and file data. The logging of these distinct socket pairs is the exact mechanism an operating system uses to effortlessly route thousands of incoming packets to the correct application tab without a single data collision. This architecture functions perfectly for data routing, but it creates an inherent security vulnerability. Because a client operating system dynamically opens thousands of these private ports to function, the local machine is highly porous. An unexplained active socket pair running in the background can indicate unauthorized, malicious data exfiltration that completely bypasses standard perimeter defenses. To expose and audit these hidden transport layer connections, IT professionals rely on an essential command line diagnostic utility called netstat. This netstat output maps the protocol, local and foreign addresses, and state for every active connection. The local address concatenates the host IP with dynamic local ports to form active sockets. The established state confirms a two-way socket pair is actively flowing. By default, netstat attempts to resolve IPs into readable domain names. Appending the command with the -n flag strips this translation away, forcing the system to display unspoofable, raw numerical IP and port data for precise diagnostics. Ensuring endpoint security requires a rigorous, active audit of the localized socket pairs that every machine relies on to multiplex the modern network.